Today, we're not going to be talking about the algorithm that we were talking about before. And I didn't even define the algorithm that we were talking about before. So today is going to be our first formal, theoretical lesson. And the reason I wanted to do this is because when I worked through the example with you last time, it was actually an easier example. And the algorithm that I'm going to leave you to figure out yourself this time. So I'm just going to show you the math. I'm going to leave you to implement it with code, hopefully referring back to the video that we had before. This algorithm is going to be even easier than that. So hopefully, if you were able to follow along with the last algorithm, the heart disease prediction and the BTS classification, then this one should be even easier. So hopefully, you should be all good to go. With that being said, let me formally introduce our big word today. So today, we're going to be focusing on an algorithm called regression, and I'll talk about how it relates to the algorithm we worked on before. Hopefully you have like a light bulb moment when you figure out, oh, that's how these things all connect. So when we talk about these types of algorithms, they really focus on two problems in machine learning. And these are not the only types of supervised learning problems. These are just two supervised learning problems. The first problem is classification. The second is regression. Now, the difference between classification and regression in simple language is when I'm trying to create a classification algorithm, the output that I'm trying to predict is one of a few possibilities. So for example, it might be a binary output. So does the patient have heart disease or do they not? Will the user buy a BTS ticket or will they not? So that's the type of problem we've been working on so far. We can also have multi-class classification. This is, for example, let's say you have an image, you want to figure out, okay, are there, a road, a car, a pedestrian, or a stop sign in this image? So now you have like four classes. That's what they're called, classes. It means the number of outputs, and you have to choose between one of these four. So classification problems, they involve, in fancy language now, what is called categorical data. You want to pick one of a few possibilities. In math, you can also call this discrete data. It's not continuous. And in comparison to classification problems, we also have this very nice, contrast with regression. Regression problems are about predicting a continuous value. So not like, okay, one of four options. Instead, it might be like, okay, predict the temperature tomorrow. The temperature is a continuous number. It can be not just, 26 degrees Celsius or 27 degrees Celsius. It can also be 26.5 or 26.55 and so on. So I hope you're seeing some of the differences between regression and classification. It's about the output. And when it comes to regression, the types of problems that we regress on, they're basically based on the relationships between the input and the output. So maybe there's like a nice linear relationship. You can just draw a line on a graph and that shows you the input versus the output. Maybe, you have a curve, you can draw a parabola, and that's the line of best fits for your data. And so on and so on. You can have cubic relationships or sinusoidal relationships, all sorts of relationships. Is this first idea making sense about these two types of supervised learning problems and the difference between them? All right. So I want to make this distinction here. This is about the problems, okay? When it comes to these problems, there are multiple ways of solving these problems. There are multiple AI algorithms that we can use to work on these problems. Now, the one problem that we're going to be focusing on today mainly is regression. And it just happens to be that when it comes to the type of supervised learning algorithm that solves the problem of regression, it just happens to be that this algorithm is also called regression. So the problem is called regression, and the algorithm we use to solve a regression problem is also called the regression algorithm. But this is not always the case. You'll see some examples later. So again, the regression problem is about taking some input data, x, and then this arrow symbol, it's read as map to. So it's like x maps to y. That's what the goal of the regression algorithm is, to take some input data x and then map it to some output data y, where the output data y is a continuous variable. So for example, when we talked about the temperature prediction, another one might be, let's take in data about a house, like the number of bedrooms, the size of the house, and then map it to the price of the house, where the output is a continuous value. That's a famous example for beginner machine learning applications, house prediction. So that's an example of how you might have a regression algorithm to solve a regression problem. So now we're going to get into the details of how regression algorithms actually work. When you're trying to map x to y, so input to output, an easy way to do that is with mathematical equations. We just want to create an equation that gives us a relationship between x and y. So for example, we could have an equation like this, where we say, okay, we're going to create some parameter, theta 1, multiplied by the x value, and then that will give us, our prediction, y hat, and we're going to say y hat is the output. So this is what we're predicting that y will be. Make sense? Following? All right. So just to make it more tangible, again, think of the housing price example. So you might have some X input data. It's the square feet of the house. Is it 400 square feet, 800, 1000 square feet? Or if you're living in the civilized world, then square meters. So is it 10 square meters, 20 square meters, or 50 square meters? Now, you can take input data like this, that's the X, multiplied by some number like, 2, and then you'd get out, your y hats or your predictions of what the y value should be. So these are the actual y values. Maybe you're predicting the monthly rent for the house. So let's say you have like a house of 400 square feet, and theta 1 is equal to, this value. Then you multiply 2 times 400 to get $800 per month. That's the monthly rent on the house. Or, for another house, you might have a different monthly rent. Another house, you might have a different monthly rent. Is this making sense as some examples of, the types of data you might work with a regression problem? Any questions so far? I just want to point out a quick problem here. This is often a problem when it comes to regression, which is that, let's say, in the US, you're measuring these input data in square feet, and in the rest of the world, you're measuring in square meters. Well, if you go and train, a data value like 2, yeah, that works, if we have square feet values, okay, 400 times 2, that's $800 per month. That's a pretty, reasonable monthly rent for a house. However, if you have, someone else come along and be like, yeah, no, I'm gonna plug in my data and they're in square meters, now you have some issues. Now you're like, what, 10 times 2? That's just $20 per month. That's not like a good monthly rent. So when it comes to the data that we use, these input features for regression algorithms, we often want to normalize the data. And that just means that we often want to make sure that all of the data, no matter which input feature it is, are on similar scales. It's not like one input feature might be, in the tens, and then another might be in the hundreds, because that's going to throw off our algorithm whenever it's training. The way that we make sure that all the data are on the same scale, we use a technique called normalization. And you can think about that context. Yeah, that makes sense. We're making sure that the data is within a normal range. So it's like we're making it more similar. The way that normalization works is that it relies on statistical techniques. So I will show you the formula that we need, even if you haven't taken a statistics class. Hopefully this isn't too complicated. The formula that we need, here it is. I know it looks a little bit messy. Let me explain it. So we have this normalization formula. What it does is it takes in an input value, x, I, that's the example. So x0, for example, that's the first example. And then it returns this value, z, at I. Z is not the weighted input. So we already used this example for what was called the weighted input in prior lessons. This is like a different variable. This is a statistics variable. So you have x as the input and then z as the output. What we're doing is we're finding the distance between this specific example, xi, and the mean. So, the average example, what is the average square footage? What is the average size of the house in square meters? So we're finding that difference when we're subtracting the two. Hopefully that's making sense. If you're subtracting any given example, you take one given example, let's say it's 50 square meters, and you're like, wow, that is big because the average house, it's only like 30 square meters. Then you're finding how far is this example from the average house size. Now on the bottom, we have this special variable. Again, I'm sorry, that the statisticians reuse like our machine learning variables, but this is the sigma variable, which we used earlier to represent the sigmoid function. But again, this is statistics, it's a different meaning. The sigma variable, it stands for the standard deviation. The standard deviation we often abbreviate as STD. The standard deviation is basically a measure of how far is the average example from the mean. Take a second to think about that, okay? So how far is the average example from the mean? This is how far is this current example from the mean divided by how far is the average example from the mean. And that kind of gives you like a sense of, okay, if we divide how far this example is from the mean by the average example, then we get an indication of how big or small is this value. Is that making sense? Some context. I'll show you how we calculate each of these things, the mean and the standard deviation, in just a second. If the average, if the current example, it were to actually equal the average, so 25, yeah, we're pretending the average is 25. So if this top bit were, the current example is equal to the mean, then that would be equal to 0. 0 divided by whatever is still 0. So that's one piece of like intuition about this formula. If the current value is equal to the average value, then the output is just going to be equal to 0. So in fact, when we normalize data, the average value that we get is 0, and then a few values that are above 0 a little bit and below 0 a little bit. So with the mean, mu, that's the Greek letter mu, this you already know how to calculate. So mu, this is just a like fancy way of saying take each example, xi, then go from the 0th example to the to like all the way up to m. That's the number of examples. So we're going like x0 plus x1 plus all the way up to like dot 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 all the way up to x. Oh, oops. I shouldn't have these subscripts. They should be superscripts. I beg your pardon. So this, sigma notation, this part just means go add up all the examples, yeah? And then we divide by m, because it's like we're taking the average. So this is just like a fancy statistical way of saying add everything up, add up all the data, and then divide by the number of data points. So that's the average, yeah? All right. Standard deviation, you're not going to like this formula. However, there is this amazing crash course video that shows you a graphical interpretation. Take a deep breath, okay? I know this is going to be messy, but there's going to be a crash course video that I'll link that will explain this for you. Here's the ugly formula. So I want to explain a few things to you. Notice this part in particular. Notice over here, what we're doing is we're taking the difference between an example and the mean. Now, this difference, it could be positive and negative. We don't, if we're adding all of them up, remember, we don't like, negative signs. So we're squaring everything so that we can get rid of negative signs. And what we're doing is then after we take the squared term, which is just like, what is the difference if we ignore negative signs, then we're adding up all of the examples. So from the 0th example, I is equal to 0 to the m minus to like all m examples, yeah? And then we divide almost by 1 over m, almost by the number of examples. So 1 over m, if we divide it by that, it would kind of be like we're taking the average of all of these differences across all of these examples. We're using m plus 1 here just for a statistical weird reason, which you'll get to hear about in the video. However, remember one last thing, since we squared everything here, we're gonna take the square root at the end, because otherwise the number is gonna be way too big. It's not gonna represent the average distance, it's gonna represent the average distance squared. So intuition again, take the difference between each example and the mean, square it so that you get rid of the negative signs, add up all of these terms, the squared distance, and then divide by a number that's almost equal to the number of data points. So it's almost like you're taking the average distance squared. And because you're taking the average distance squared, then take a square root at the end so that you get rid of the squared. So you find the average distance between any points and the mean. This is a complicated formula to understand, so there is this amazing crash course video that will show you why this makes sense. However, the key idea is we just use this formula to, we find the standard deviation, we find the mean, mu, we plug in these values, and then we use this formula with every single example so that we can get out some normalized data that looks a little bit like this. So Z is going to equal to 0 if, don't worry about it, conditions, and then 0.4, negative 0.9, just a bunch of data that's very close to 0. Hopefully that's some intuition. I'll give you a link to a crash course statistics video so that you can learn those basic statistics. But the key idea for us in machine learning land is here's the formula, here's how you compute, the mean mu and the standard deviation sigma, so that we can use this formula. We pass in all of the x's, so all of these inputs, and we'll always get some data that is very close to 0. In fact, 68% of the data is going to be between -1 and +1. That's a very precise number, I know. Wow, that's a magical secret. Math, yay. Anyways, I'll link to like a statistical video that'll show you exactly why this is true. So basically this is a function that makes all your values go from -1 to 1 mainly. Cool? We do this so that we can just train the algorithm on some normalized data instead of, some data that has wildly different ranges and scales, so that the parameters that we train are more generally applicable. Now, technically speaking, we'd call it this big, vector Z. However, yeah, I'm lazy, so we're just going to call it X still. Just keep in mind that this X now has been normalized. So we took every one of the X examples, Xi, and then we've performed this operation, and now we have like this normalized vector X. And now we have the same relationship as before, where theta1 is some scalar, it's being multiplied onto a vector. Remember, that just means element-wise multiplication. And we're getting out this other vector, which is made of continuous values, not discrete values, not like, oh, it's either a bike or a car, but instead it's made of, oh, the house price is $450 per month to rent. Making sense? All right, take a breath. That's normalization. That's a very important part of regression work. You should always normalize your data, especially when it can be on different scales. Now, here's the issue. This is a really simple relationship, because like it's just like, oh, you have one setting, theta1, and then you multiply by whatever input. That's not much room for the algorithm to learn. There's not even much room to get like a proper linear relationship. Remember, like a really linear relationship would be like y is equal to mx plus b. Yeah? Here we don't even have like a b. We're not even adding anything. Why don't we try adding something? How about that? So we're learning like a more complicated regression function here. So this would be a directly proportional relationship. That's what it's called in math. We can also make this relationship more complicated. I'll get to this in just a second, but we can also make it more complicated by doing something like so. So we add theta1 x1, and then we might add like a second parameter, theta2. So that would be like a fully linear, relationship. Over here, this is directly proportional. This is fully linear. Yeah? So we can make regression more complicated if we want. Making sense? We're going to talk about some of the implications of this as we get into the next parts of any AI algorithm. We got to figure out some way to measure the performance and to be able to update these datas, these parameters, so that we can decrease the cost over time. So first of all, measuring the performance. Hey, we have our good old cost function, mean squared error. Remember this? Yeah? In this case, this actually works great. So this cost function, mean squared error, this is a great cost function for regression problems. Now, we'll have a lesson, probably the next lesson in fact, where we'll talk about some other cost functions, but for now, this is working great. Let's just keep it. The other thing we got to do is remember gradient descent. We got to update the algorithm's parameters, so theta1, with this rule. Theta1 is equal to theta1 minus the hyperparameter alpha, the learning rate, times the partial derivative of c by partial theta1. Remember this? Now, to get this term, to get the value here, well, remember, we gotta use the chain rule. So partial c by partial theta1, that's equal to partial c by partial y hat, because of this equation, times partial y hat by partial theta1, because of this equation. Yeah? And remember, these cancel out, so you're still left with the same thing. Hopefully this is not new. Again, you could literally pause and look at this expression, and if you go back to the derivative videos, the calculus videos, you'll see how to calculate the derivatives in both of these cases. However, the end values that you end up getting are 2 times y hat, the prediction, minus the label. That's from this equation. And then xi, that's from this equation. And remember the subscript I over here, that means, for each training example, and we're going to go and take the average across all the training examples. That's what this means. Sum over all the training examples, then divide by the number of training examples, take the average. So over here, we are modifying theta so as to decrease the cost the most for the average example, not just, for one training example I. Is this sort of familiar? Is this making sense? Now, I did want to tell you where this, xi thing is coming from just for a second. Remember, if we have this relationship and we take a partial derivative, you can go back to that lesson, but if we're taking this partial derivative over here, this just means, take all of this and figure out, okay, what is partial of by partial theta 1? That's a theta. There we are. Of all the stuff, that is right here, that y hat is representing. So theta 1 times x1. This is what that term means. And if you think about this, remember what we said in the partial derivatives lesson, you just treat every single other variable like a constant. So it's just like, okay, constant times theta 1. What is the derivative? Well, okay, it's like, okay, theta 1 raised to the power of 1 times this constant. So you take all the constant stuff over here, x1, and then you multiply that by theta 1 raised to the power of 1 minus 1. Theta 1 raised to the power of 1 minus 1, which is 0. And this is just equal to 1. Yeah? So in the end, you're just left with theta 1, with x1. And this is for the ith example. Hopefully some of that makes sense. If not, feel free to review the partial derivatives lesson. But basically, we're taking the coefficients here, and that's how that coefficient is how we get this xi value. Sorry, this is the coefficient of theta 1. I see a blank face, but yeah, that is unfortunately what we are doing. How are you feeling? Okay, so you're bored with it once, that's the algorithm part of the algorithm, plus, this normalization bit that complicates things. And then the rest is the same. You just have the cost function as ever, you just have gradient descent as ever, just have annoying, derivatives, back propagation as ever. And you can go and take these equations now and look at how you can implement this in code. And that would be your first regression algorithm. Yeah. Wow. That would be your first regression algorithm with this like simple relationship. So these are the equations you need. You can translate this math into code. Now, as I said, this is a bit of a limited equation. So I'm going to show you some other equations and then we'll call it a day. That's the end of regression. Just some more fancy equations here and the rest of it is the same. For now, just remember that these equations that you see right here, with all of this, you can go code everything you want. So you could code this regression algorithm right now, just with these normalization equations, just with this relationship, cost function, and gradient descent and backpropagation. So everything you see on screen is right here for you. You could translate this math to code. The only thing is that this relationship is a little bit simplistic. So I'm going to show you some other relationships, because maybe you can't find just one coefficient that lets you perfectly go from theta 1 and some input feature to the prediction that you'd like. So the first thing, which I hinted at earlier, why not just make like a full linear function, mx plus b, or theta 1x plus 2. If we can do that, we get like an added layer of complexity. Our algorithm can more directly, cater to the needs of our relationship. So if we do that, then same thing happens. We're still gonna go through the cost function. Yeah, we're gonna get our like output prediction y hats, go through the cost function, and we're still gonna do gradient descent. Theta 1 is equal to theta 1 minus and all of that. Again, this is the equation that we need to calculate this term. However, we do have one quick difference here, which is that there is no longer a coefficient being multiplied here. So there's no longer, coefficient associated with theta 2. It's being added. So when we perform gradient descent, still the same equation for gradient descent for theta 1 and 2, but since this term it has no coefficient, we have a slight change of plans when we do the backpropagation. So when we, take the chain rule, it's still the same chain rule as ever, same thing as up there somewhere. Same thing as up here with the y hats canceling out the predictions. But the only difference is this term is now different, because this term is now no longer being multiplied by a coefficient. And think about why this makes sense, okay? So we're saying take the partial derivative of this business right here with respect to this variable. So if it's with respect to this variable, then automatically all this stuff gets crossed out. This is like treated like a constant, yeah? So that gets crossed out. Over here, this is like saying, theta 2 times 1. So that's why we, in the end, get a 1, because it's like there's a coefficient of 1 here. So this corresponds to this 1 over here. If you're confused, go back to the partial derivatives and derivation lessons and you'll see why that's the case. But even if you don't want to do that, then in the end, it's pretty simple here. What you need to take away is that we just have the exact same thing happening with this more complicated function as we did over here. It's just that when we're computing the derivative, this term, during backpropagation, then the formula for computing that is different. It has a 1 here instead of the coefficient x. Is this making sense? Now, that's like one level of complexity. We can keep like expanding upon that. So let's say like we had x, it was a 1000 by 4 dimensional vector. So 1000 is the number of examples, the number of houses, and 4 are like 4 input features about the houses, number of bedrooms, number of bathrooms, the size of the house, the neighborhood, for example. So we could take, this x, which has more input features, and we can, correspond them with more parameters, theta 1, 2, 3, and 4, that correspond to these 4 input features. And then like a 5th parameter that we add on in terms of, just like we added on theta 2 here. It doesn't correspond to like one input feature. That's why these ones are all in cool colors. This one's in red because it's being added on. It's like technically separate. Here's an example of the relationships we could create. So we could do the same thing as before. We could do theta 1 x1 plus, in this case, theta 5. Before we just called it theta 2. You could still do that if you wanted to, or you could get more rich. So you could do theta 1 x1, the number of bedrooms that returns a scalar number. You could do theta 2 x2, the number of bathrooms, theta 3 x3, housing size, number of square feet, whatever. This might be the age of the house, and then, some random parameter that we train, theta 5, and that's like even a more complicated regression equation. Is this making sense so far? So we're still doing the same thing as before, we're just making our function more complicated, more detailed, so that it can more accurately predict the monthly rental price of the house. And again, you can literally go code this yourself right now. And same thing as above, like this would be the backpropagation for the constant theta 5, and all of these you would use the backpropagation equation over here. And then aside from that, everything else is the same. Now, this is all linear up to this point. I did mention at the beginning quadratic equations, cubic equations. The way you could do that is by having this kind of relationship, where you not only have, the say number of bedrooms, you have the number of bedrooms to the power of 4, and the number of bathrooms to the power of 3, and the number of, let's say, the square feet squared, square feet squared. Or maybe let's say you just got like, the feet, and then you needed to square it for some reason. And then maybe this one is to the power of 1. So you can make like more complicated relationships. How do you get x1 to the power of 4? Well, you could literally just take x1 and then, replace that input feature with x1 raised to the 4. So for each example you have, each training example, this is not, this literally means, raised to the power of 4 this time. It's not like the 4th example. Each training example you have, you could raise it to the power of 4, and then it's like you're creating a new feature. Instead of the number of bedrooms, you have the number of bedrooms raised to the power of 4. So instead of like, this is a 2-bedroom house, now it's like a 16-bedroom, like 16 bedroom to the 4th house. I know that seems convoluted in this case, but there are instances where you can get a more complicated function. You can get a more complicated regression equation because of this. This is called feature engineering. It's kind of like you're engineering your own new features from x1 to x raised to the power of 4. And you can go overboard with this. Like you could create an equation that looks like this, theta 1 times the sine of x1, and then, cos of x2, and then over here, you take the log of the square root of x3 and raise it to the negative pi. You could do that if you wanted to. I wouldn't recommend it. It doesn't seem like a good idea. But it would be the same principle. So you would take x3 and like replace it with the feature you want computationally. And you would do this beforehand. That's how you might implement something like this if you wanted to. Arjun?
How would we know when to feature engineer for better accuracy?
Yeah, this is first thing first, don't feature engineer unless you need to. Okay, that's the first rule. Number 1 rule, don't do it unless you need to. So if you like, just run this version, this simple algorithm, and you figure out, oh, hey, I'm already getting, 95% accuracy, or my cost is like going down so much, and yeah, then do not feature engineer anymore. So that's the basic rule. Keep it as simple as you can when you're starting off. And then after that, there are some very specific theory tools that we're going to learn about on Monday that are going to talk about how do you compare whether this relationship is doing better than this one, for example. And it's going to have to do with graphing and visualization. It's going to be very cool. So I'm very excited to talk about that later. For now though, go crazy. So you have all these equations. I'm showing you the math. Go try coding it out, go make it like, oh, theta 3 log, log of the square root of the third feature raised to the negative pi. You'll figure out, oh, how do I actually get the value of pi in Python? Maybe that's something you don't know yet. So just go crazy for now. And on Monday, we'll talk about when do you actually use one equation versus the other. Cool? So with that being said, that is it. This is done, regression. I did quickly want to add in something here, which is earlier when we were working on those algorithms for getting a binary classification, like will the patient get a heart disease, we were using an algorithm called logistic regression. The only difference between regression and logistic regression, as you can see, is this sigmoid function. Because, we're calculating this, remember these equations, the weighted input Z, it looks pretty similar to what we're doing up here. And then the y hat is just like a rounded version of this activation. So the only step that's different is this step. And the reason why this algorithm is called logistic regression, it's because the sigmoid function, it has an alternative name. It's called the logistic function. So logistic regression just means regression, except you take the output and run it through a logistic or a sigmoid function. Remember, the sigmoid function just returns like 0 to 1 range, which is good because then we can round it to like either 0 or 1. So we can make that prediction, binary, 0 or 1. Cool? You see? So logistic regression is just like a fancy version of regression. Hopefully that gives you some context as to what we were doing before, and what we're doing now. So this is like a simple version of logistic regression because we don't have this sigmoid or logistic function here. Arjun?
How would logistic regression be a regression though? It's like classifying between like two discrete variables.
So because we call it logistic regression because this first step is just regression. It's the same thing that we were doing earlier. Just take a bunch of data, multiplied by, x's, and this weighted input is still like a continuous variable here. This weighted input, it's a continuous number. It could be 100, it could be 100.5, and so on. The only thing that's different is now we add on this logistic part, which is we take this logistic function, this sigmoid function, logistic means sigmoid, and then we turn this continuous variable into a categorical variable. Yeah?
Yep.
So hopefully that gives you some context as to what we did before versus what we're doing. Well, what we did before was this, logistic regression, and this is an easier version of that. So hopefully that helps your confidence a little bit. Remember, you have all of the tools you need right here. If you wanted to implement, again, here's the normalization equations. Here are the ways you can formulate relationships, whether you have functions that are complicated or whether you have functions that are simple. Here's the cost function as ever, gradient descent function. And this gradient descent function over here, if we're getting the value for, a parameter that's being multiplied, we use this version. If we're getting the value of a parameter that's being added, then we use this version. Cool? So all of the equations right here, you can go look at the notes. It will be attached in the recording. And I wish you the best of luck in coding things. That is the end of this lesson. One final note very quickly. When you're practically coding, it might be nice to not, get, a input feature and replace it with this value. You might maybe create like a new variable that stores this new information, just so you have like the original data. Let's say you wanted to change it. Another thing is, let's say like you're taking the derivative of this function when you go and look at, the coefficients, in this case, the coefficients would turn out to be x1 raised to the power of 4. However, you don't need to go and raise the value to the power of 4 again. Reason being, you already replaced x1 with x1 raised to the 4. Get what I'm saying? So don't be like, okay, yeah, like I'm gonna first go take x1 and replace it with x1 raised to the power of 4, and then I'm gonna do it again, when I'm doing the backpropagation calculation. By the time you get here, x1 is already equal to x1 raised to the power of 4. So you don't need to, raise this value again. Do you get what I'm saying? Just do it once at the beginning. So with that being said, that is it. Go check out the recording afterwards. You'll see all of these equations and all of these notes. And I will leave you a Kaggle dataset that you can download and work on, where I will have pre-processed some data for you so that you can work on things easily.